Hello everybody, I am happy to see you again. Today we will talking about static force analysis. We use machines to apply mechanical force, energy, or power for a useful purpose. So far in this book, we have been concerned about motion. Next step, the force acting on the machine will be taken into account. In many applications, their motions are negligible. Therefore, they are usually regarded as static machines. In this chapter, static force analysis is conducted to determine the force of the mechanisms. We skip some sections, only discuss section 14.1 to 14.6, 14.9, and 14.10. We will talk about two methods, free body diagrams and the conservation of power. I think they are useful tools for static force analysis of the mechanism. If dynamic effects are not involved, we can analyze mechanism using the equation of the statics. Sometimes their functions are without motion. If the velocities of their motions are small enough, that dynamic effect can be neglected. For example, clamps, pliers, and the heavy lift device. It is necessary to determine the loads throughout a mechanism to allow the designer to ensure that the parts are strong enough to avoid failure. Software packages are available to conduct force analysis on mechanisms, ADAMS for example. However, it is still necessary to occasionally conduct a manual analysis to ensure that the programs are giving reasonable answers. The purpose of force analysis is to calculate loads of the mechanism. According to the laws acting on links, we can design dimensions of links to make sure the strength of links is enough. The input force of torque needs to figure out to select a proper motor to drive the machine, and determine the output force for torque to obtain the transmission capacity of the machine. There are two methods adopted here, free body diagrams and the conservation of power. I would like to talk about force briefly. A force is a vector that has magnitude and direction. We can express the force in rectangular components of a vector. They are x, y, and z components. For example, force F1 has a magnitude of 5,000 Newton, and the angle between force F1 and the three axes are 16, 45, and 16 degrees. So the x component of force F1 is 5 times cosine 16 degrees. The y component is 5 times cosine 45 degrees. And the z component is 5 times cosine 16 degrees. Force 2 has only the y component, minus 2,000 Newton. If two forces A and B have intersecting lines of acting, they can be summed into a single force A plus B by the triangle construction. Let's see a couple. Two equal and opposite forces. They are collinear will sum to 0. However, two equal and opposite forces, they are not collinear will be a resultant force is 0, but will form a couple. we determine the moment of couple M by vector R cross vector F like this. Its magnitude is h times F, where h is perpendicular distance between the two forces. Moment of force is often called moment of torque. A single force will generate a moment about a point P. Moment can be given by the cross product of the position vector R and the force vector F, where the position vector is a vector from the point above which the moment is being measured to the point where the force is applied. For special problems, we have three components of moment, like this. The magnitude of moment can figure out by the force times the perpendicular distance Rn from point P to the line of action of F. The distance Rn is also called moment arm, and is perpendicular to both vectors and F, following the right-hand rule. In parallel systems, the first two terms of moment equal to 0. The moment is in this direction, and its magnitude is the sum of x times Fy and minus y times Fx. We can replace a force and moment by an offset force. The effect of a force F and the moment M applied to a rigid body can be replaced by a single force offset from its original position by a distance h. H can be calculated using the magnitude of M divided by the magnitude of F. Of course, force problems always be solved by Newton's second law. In the static or dynamic force analysis, Newton's second law can be applied to determine the laws. In the second law of motion, the particle will accelerate in the direction of the force. If the mass is m, the magnitude of the acceleration is directly proportional to the force. Multiply both sides of the equation by the radius r, you will obtain the equation of the second law of rotation. Radius r times a force F is a torque. The net external torque on the object is equal to its moment of inertia, I, about the rotation axis, times the angular acceleration, alpha. The torque will increase or decrease the object angular velocity according to the direction of the torque. The torque is the rotational equivalent of linear force. It is also referred to as the moment of the force, rotational force, of turning effect, depending on the field of the study. For the static mechanisms of the mechanism with the negligible dynamic effect, static equilibrium will be taken into account. We may say that a body is in static equilibrium if it remains in its state of rest. From Newton's first law, a body is in static equilibrium if the resultant of all the force acting on the rigid body is 0. This condition results in two vector equations. The vector sum of all the force acting on the body is 0, and the vector sum of all the moments about any arbitrary point is 0 too. In space, these two vector equations have 6 scalar equations of equilibrium, x, y, and z components of the force and moments. However, in this lesson, we only concern planar mechanisms, so we will have 3 scalar equations, x, y components of the force, and the z component of the moment. In mechanism, there are 2 force members, 3 force members, 2 force and 1 moment members, and so on. This figure describes the 2 force member in equilibrium. When a rigid body acts on by 2 forces in static equilibrium, only if the 2 forces are the same magnitude. They are act along the same line and in opposite directions. In this situation, the force vector F1 is equal to the force vector F2, and no moment acts on it. This slide shows a 2 force and 1 moment member. A rigid body acted on by 2 forces and 1 moment is in static equilibrium. Only if the 2 forces are equal and form a couple whose moment is equal in magnitude, but the opposite direction to the applied moment n. The slide shows a 3 force member. A rigid body acted on by 3 forces is in equilibrium only if the forces are concurrent and the resultant is equal to 0. It means that 3 force lines of action are intersected at one point O, shown as figure A. They can be represented in magnitude as well as direction by the 3 sides of the triangle taken in order, such that its sides are parallel to the direction of the force respectively. They are shown as figure B. As head of the last vector F3 meets the tail of the first vector F1, the resultant will be to 0. Figure C shows a case where the magnitudes and the directions of the force are the same as before, but the lines of action of the force do not intersect at one point. In this case, the member will not be in equilibrium.